Instead of completing the square on this problem that we were working on Tuesday, I decided to change the problem. So uh, I changed the third term to a 9 instead of a whatever it was before, a 3 maybe. So um, given that, you should be able to factor it without using completing the square. That was kind of distracting from the technique. So instead of distracting from the procedure. Before we start that, though, remember the test is next Tuesday. It's on Chapter 2. I have posted the review on YouTube. It's about 30 minutes. I also made up the test and took the test myself to find any errors. So it's took me about 18 minutes, which if you multiply that by 3, you get about an hour. 4, you get an hour and 15 minutes. You'll get a whole you'll get as much time. Well, not as much time as you want. You'll get till about quarter till 10, so you'll get an hour and 45 minutes to take it. It should take you about an hour, but for you slower people, you'll have more time. So, like normal, you get to bring in one cheat sheet. Anybody have any questions about the test? Okay. Oh, before I was going to wait till tomorrow. Well, I thought of waiting until tomorrow, but I was yesterday after my math for the liberal arts class, I reran the physics experiment because I was curious about the large percent error that we got in the third part. And so I got the same kind of thing. Especially if you used a low mass to do your experiment so it didn't accelerate quickly up, and we accelerated the block up the ramp. If you accelerated it quickly by using a heavier mass, hanging mass, you got still a reasonable error, but not too bad. I got like 12% when I did it, but when I used lesser mass and it went up slowly, I got a huge error. And I finally figured out what it was. So what I did was I calculated the coefficient of friction going up, which is, a few people did that. So remember what we had done was we calculated the coefficient of friction of the block going down the ramp, and then we used that to calculate the acceleration going up the ramp and compared that with the measured acceleration. They didn't agree very well, and the reason was I was puzzled, and then I picked up the block and I looked at it, and I was feeling the felt, and I go, huh, this is like carpet. It has a direction to it. So it has a nap. So the reality was that the friction going up was less than the friction coefficient going down. So when you used the one going down, your calculations going up were not very accurate, and they were less accurate when you had less speed because the friction force relative to the other forces was bigger, and so it kind of swamped things. So I've got to remember to do this. So next year, so I don't mess this up, what I'll do is the third part of the experiment will calculate the friction coefficient going up, and we'll compare it with the friction coefficient going down, and I can say, oh, and notice the nap of the carpet or the felt on the bottom, and they'll be just amazed. No, they won't, but at least I won't confuse you all with the huge percent errors that you came up with. Because I think you remember it and you noticed that the ones that didn't involve the friction were the percent errors were much less because there was less, it was more idealized, and therefore you didn't have to worry about things like that. Okay, so remember what you're doing is you're going to take the derivative of the function. You're going to set it equal to 0, factor the first derivative, find out the values of x where the derivative go to 0. Those will be your critical numbers. Then you evaluate the function at those critical numbers, which should be in the interval. You'll also evaluate the function at the endpoints, which are these points. And then you figure out what is the biggest number, that's the maximum, which is the smallest number, that's the minimum. So we'd gotten to the derivative part yesterday, but you're going to have to redo that because I decided to try to make this easier on you guys, factoring wise. The other, the other place critical numbers are when where the function is the derivative does not exist. In this case, the derivative exists at all values of x, so we don't have to worry about that particular case. So how many people have made homemade caramel, like little soft caramels? Anybody ever made those? I'm thinking of trying that, bringing some in to share. Might be able to handle that. It was caramel. It was actually, yeah, it was Caramel Week on the Great British Baking Show. You love that show? So they've moved it from BBC to Channel 4, and so there was a big controversy about that. I have not actually seen the show. I listened to the radio, and they were talking about making caramel. I thought, I need to make caramel. There's a thing, a dessert in England it's called Millionaire's Shortbread. Has anybody ever heard of that? So what it is, it's like a shortbread, base, and then you put on this kind of soft caramel as a layer, and then on top of that you put chocolate. It's good. Very decadent. So take the derivative, divide by 3 to get rid of this coefficient in front of the x squared term, factor it. So when x equals -3, this is 0. When x equals -1. So those are your critical numbers. So now you need to find the critical numbers at x equals -3. Well, not the critical numbers, the y values. Evaluate the function. So evaluate the function at -3, -1, and then at -6 and +3. So you'll do f, not f prime. Some people make that mistake. They evaluate the function at the derivative at those, and they find out they're 0, and they're like, huh, something's wrong. So I'll let you do that work. Plug it in, use your calculator. Oh, you forgot my calculator? Oh, you can use mine then. Yep. Yeah, you can check with your neighbor, see if you got them right.
I thought, like, if you took a 3 out, you had to have 1 is x equals 0. Like just a regular number. Like without a variable.
Oh, this part here?
Yeah.
Oh, you think there's 3 solutions?
Like,
if you factored on an x, let's say it was x cubed, and this was x squared, and this was x, and then you had a constant, well, no constant, then you could factor out an x. So it's only when your 3 terms here all have an x involved where you factor it out. The 3 doesn't do anything as far as zeros are concerned. It just, what that 3 does is it just stretches the graph in the vertical direction, but the actual intercepts of this function, the derivative, the function that the derivative represents, they stay the same if you factor out a constant. If you factored out an x, then you would have one. Oh, I'm gonna do something that's, don't do this, but I'm gonna explain why. I'm doing it in a second. Okay. It's just a little side piece of information. Oh, wrong thing. No, that's right. Yeah, right. Let's see what Jacob's got. What'd you get for f of -3? Oh, how about that? So what I did there was when you divide the original function, well, when you use long division, not long division, synthetic division with the original equation, and you don't get a 0 at the end, it means that -3 is not a factor of the original equation. But what it means is that the remainder, which is -10, is the value of the function. I don't know if you remember that from pre-calculus or not. But the nice thing about it is actually you don't have to cube anything, or you don't have to square anything. So if I were doing this, whoops, sorry. If I didn't have a calculator, I think I'd use synthetic division to get my answer rather than doing multiplying out -3 to the third power and adding it to 6 times -2, 3 to the second power, and so forth. So just because the actual mathematics involved is a little easier because you don't, like I said, you don't have to use you don't have to cube or square anything. So let's just prove that works again. So if I put -6 in there, you'd have 1, take this down, -1. Well, I got to erase these parts too. I just have to do multiplication and division, subtraction. Bring that down. -6 times 1 is -6. Just add those together, you get 0. -6 times 0 is 0. Bring that down, that's 9. -6 times 9 is -54, and you add those together and you get -64, which should be the answer there. Is that right? Yeah. So just to, I'm not going to ask you to do this, but it's kind of I found through my years of teaching these things that that's an interesting use of synthetic division, especially if you can multiply things in your head, at least reasonable numbers. 27 times 9, 27 plus 9 is 36. 36 times 3 is 108. 108 plus -10 would be 98. Is that right? And then the last one is -1. So -1, bring that down. -1, 5, -5, 4, -4, -14. Okay. So those are the answers. And so what is the absolute maximum? Asia. What's the value of the function? Yeah. So if I said what's the absolute maximum, you'd say the absolute maximum is 98. It's at the end point, and the absolute minimum is actually here. So it turns out that just because I changed this without, in this case, the extrema are at the endpoints. These are local extrema, but they're not absolute extrema. If we plotted the function, let's see what it looks like. So the function is x cubed plus 6x squared plus 9x minus 10. And I got to zoom out a little bit. Okay, minus, minus, minus. There we go. So you see we have an x-intercept here, just have one x-intercept. And a -3, which is about right here. The value of the function is -10, which is, oh, right here. And then you have a local minimum here, which is the one at x equals -1. But because of the interval I chose, which was from -6, the actual the actual absolute extrema are the endpoints. Usually what I'll do in the test is one will be at the endpoint and one will be at one of the extrema, the local extrema. Okay. Okay, now that's one class of problems, which is polynomials, and those are pretty easy, especially if the derivative is easily factorable. If it's not easily factorable, you can use completing the square, or you can use the quadratic formula to find the actual roots. So actually, let's go back and just do the completing the square for this previous problem, except I'm going to change the numbers back to what I originally had, and just to show you how to remind you how to do completing the square to solve for the zeros. So if my original function was x cubed plus 6x squared plus 3x minus 10, like we originally had, the derivative would be 3, whoops, I'm not drawing very nicely here. The derivative would be 3x squared plus 12x plus 3. And if I set that equal to 0, I'm setting it equal to 0 to find the values of x where the derivative goes to 0, because those are critical numbers. So I divide by 3 again, and I get that, which you can't factor easily. So especially if the x term is an even number, completing the square is pretty easy. So what you do is you take, I'm just going to switch sides here. I like to start off with it on the left-hand side. You take the variable part, separate that. You take the coefficient in front of x, you divide by 2, and you square it, which 4 divided by 2 is 2, 2 squared is 4. So I add 4, and then I subtract 4, and I set that equal to 0. So I'm adding and subtracting the same thing. And then I change this into a complete square, so that would be x plus 2 quantity squared minus 3 equals 0. So I combine those two. Then I add 3 to both sides. And I get that. And they take the square root, so I get x plus 2 equals plus or minus the square root of 3. And then I subtract 2 from both sides, so I get x is -2 plus or minus the square root of 3. So those are my two solutions. Those are my two factors, or they're my two values of x where the first derivative goes to 0. And it's always centered around here. -2 turns out that'll be a special number, but we have to wait till 2 more sections to figure out what that number -2 means. But the zeros are symmetrically, the zeros of the first derivative are symmetric around this number. One's square root of 3 to the right, and one's the square root of 3 to the left. So that's how you would have solved the problem if I hadn't rewritten it. And you could also use the quadratic formula and get the same result. Okay. Now, the second kind of problem that we're doing is finding the critical numbers associated with trig functions. And so I'm going to show you a technique that I use that Mr. Appel doesn't use as much. Even I told, he said, what should I emphasize? And I said, reference angle. He probably may or may not have done much. So does anybody remember what the reference angle is in trigonometry? See who's looking down. No, just kidding. That's what I usually do when I don't know the answer. Look down so nobody will call on me. You won't call on me. Okay. How many people know what the reference angle is? I won't call on you if you raise your hand. I'll tell you what it is. Does anybody remember what the reference angle is? Okay. Okay. Maybe. Okay. So we'll see if it's what you think it is. Yeah, I don't want to. I just wanted. I didn't want anybody to say he said he wasn't going to call on me if I raised my hand. So. Yeah, so here's a story. I'm probably doing it. So, there are certain people who blush easily, and I'm probably blushing now because when I talk about it, I do it. Okay, I think. So anyway, you know who you are, and so I would, when that would happen in class, and I didn't know the answer or something, I don't want anybody to. Don't call me, and then they would call you. Then I would turn red, which was always embarrassing, but I can't help it. So it's a flaw. It's my wife used that to her advantage when we were in high school. So I moved from Ohio to Virginia between my sophomore and junior in high school, and Martha was in my American history class, U.S. history class, as a junior, and she sat in front of me. So of course I was the new guy, and she's very outgoing, as most of you who've had her know. So she turns around and says, "Hi, who are you?" And I'm probably turning red, and she used to. So we started dating our senior year in high school. But she said she used to tell her friends, "Look, I'm going to say hi to Steve, and he's going to turn red." And I would. So it's true. Anyway, that's so if anybody has that affliction, I have sympathy for you. Okay. So the reference angle is, if you remember angles, just angles in general, you had angles. Let's say we're measuring them relative to the positive x-axis. So this would be theta, the angle between the positive x-axis and some ray that's going from the origin. Now, if I had a second angle that, let's say, went this way, let me use a different color. I'm just going to have to draw it in. So here's another ray. This is in the second quadrant, and the angle is this angle. So this is, let's call that this theta 2, and this is theta 1. The reference angle is the angle between the ray and the nearest x-axis. So this would be the reference angle relative to theta 2. So in the first quadrant, the angle is the reference angle because the closest x-axis is the positive x-axis. So in this case, theta 1 is the same as the reference angle. But for theta 2, the reference angle is less. The reference angle is always less than 90 degrees because wherever the angle goes, the line goes out, the nearest x-axis is going to be less than 90 degrees. So in the third quadrant, the reference angle would be here, whereas the actual angle would be all the way from the positive x-axis. And then in the fourth quadrant, you measure the reference angle relative to the positive x-axis. So if this angle were, let's say, 200 and 300 degrees, which is in the third quadrant, that'd be about right here, the reference angle would be 60 degrees. So depending upon which quadrant you're in, the reference angle can be related to um, the regular angle in this manner. So I'm going to, Q stands for quadrant. So in the first quadrant, the reference angle is equal to the angle that we're measuring or we're referring to. So like here. In the second quadrant, the reference angle is equal to pi minus theta. So we're talking about radians here. So pi. So get your radian hat on. Okay. So in this case, if this were, so this is pi over 2 radians. So if it was, say it was 3/4 pi, 3 pi over 4, which is in here, the reference angle would be 1 pi minus 3/4 pi, which would be pi over 4. Okay, in the third quadrant, the reference angle is equal to pi plus, sorry, what am I doing here? Make sure I'm doing this right. The reference angle is pi minus theta. Hold on just a second. That's right. Yeah, theta minus pi. So if this is in the third quadrant, then the reference angle is theta minus pi. And the fourth quadrant, the reference angle is equal to 2 pi minus theta. And you can go the other direction too. You know, you can say theta in this case is equal to pi minus the reference angle. In this case, theta is equal to pi plus the reference angle. Here it's the same. It doesn't change. So in this case, theta is equal to 2 pi minus the reference angle. Okay, I've just solved the equation for theta instead of the reference angle. Okay. Why are we doing all this stuff? Is because sometimes you have solutions that are in the quadrants other than the first quadrant. And if you have a calculator, wherever I put my calculator, oh, you have it. So, you know, when you do the inverse, we're going to use the inverse trig functions to figure out what values of pi or theta make the derivative go to 0. So we're going to find the roots of trigonometric equations. And one way is to memorize the unit circle, which is great if everything were made of objects that had 30-degree angles and 45-degree angles and 60-degree angles and 90-degree angles, but that's not the real world. So in the real world, you don't really use the unit circle that much. I hate to disappoint you that you had to do all that work memorizing the unit circle, but interestingly enough, when I don't remember the unit circle at all. I may have had it, I don't remember it, because I never used it in 9 years of engineering classes. I used my calculator to calculate angles. But the problem with using your calculator to calculate angles using the inverse trig functions is that the domain of the range of the inverse trig functions are limited. If you take the inverse sine of some number between 0 and -1, you'll get an answer between negative 90 degrees and positive 90 degrees, or negative pi over 2 and positive pi over 2, which is okay, except what about solutions that are in the second quadrant or the third quadrant? It doesn't automatically work. So if you just blindly put in inverse sine or inverse cosine or inverse tangent to solve these equations, you may not get the right answer. You might be in the wrong quadrant. So we're going to use the reference angle and the sine plus or minus of the trig functions to figure out what quadrant you're in. We're going to use the calculator to calculate the angle, the reference angle, and then we're going to use these formulas to figure out what the actual angle is based upon what quadrant it is in. Okay, so that's the background here. So we're just going to give you an example. So here you might have had this in pre-calculus. So the sine of x equals negative the square root of 3 over 2. So the question is, what are the values of x such that this equality holds? So you could use the unit circle in this case, because that's one of these, that's the sine of some angle that are 30, 60, 90, or pi over 6, pi over 4, pi over 3. But I'm going to show you the technique to using your calculator and using reference angles instead of using a unit circle. Okay, so the first thing you do, first question is, in which quadrants is the sine negative? Not sine with a G in. That was dumb. The sine negative. So has anybody heard of all students take calculus? You're in calculus, so you're like, yeah, well, not all students take calculus. Anybody here, did anybody ever use that? Yeah. So that stands for quadrant. So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So, and then you've got sine, cosine, tangent. So in the first quadrant, the sine's positive, the cosine's positive, the tangent's positive. In the second quadrant, the sine is positive, the cosine is negative, and the tangent is negative. In the third quadrant, the sine is negative, the cosine is negative, and the tangent is positive. And in the fourth quadrant, the sine is negative, the cosine is positive, and the tangent is negative. So the way this thing works is, in the first quadrant, all of the trig functions are positive. In the second quadrant, the sine is positive. In the third quadrant, the tangent is positive. And in the fourth quadrant, the cosine is positive. So by looking at that, or you can use the unit circle, but you don't have to write any numbers on it. You just have to think about. So the other way of thinking about this is, which is what I used to do. This was actually, it was Claire Sackner. Remember Claire at all? Yeah. She told me that. She says, "Oh, all students take calculus." I'm going, "What?" She says, "Yeah, that's how you remember that." And I go, "Oh, okay, yeah, that's pretty cool." So we are all never too old to learn something new. Okay, so what I did was, what you remember is the y coordinate in the unit circle is the sine, and the x coordinate is the cosine. So in the first quadrant, y is positive and x is positive. And because these are both positive, the tangent's going to be positive. Okay, so that's how you would do the first quadrant. In the second quadrant, so they're both sine and cosine are positive. In the second quadrant, the sine is positive because y is positive, but x is negative. So in this case, the sine is positive, but the cosine is negative. And because these are different signs, the tangent's going to be negative. In the third quadrant, they're both negative. Since they're the same sign, the tangent's positive. And in the fourth quadrant, the y coordinate, I'm doing y then x, which is because it's sine, cosine. In the third, here it's plus, it's minus plus. So y is negative and x is positive. So sine is negative, cosine is positive, so the tangent's negative because they're opposite signs. And that's how I remembered it from a picture standpoint. Just thinking, all you have to remember is draw a circle, know that the y value is equal to the sine, and therefore x has to be the cosine by default. Think about what the sine of the different coordinates are in the different quadrants, and you can figure it out from there. So either way, so given that information, let's see, who am I going to ask here? Jacob. So in what quadrants is the sine negative? Yep. Okay, so we know that our solutions are going to be in the third and fourth quadrants. So the problem is that if I use my calculator and I put it in radians, so I'm going to put in radians here, and I take the inverse sine. So to solve for x, I could take the inverse sine of both sides. So I'm going to take the inverse sine of, oops, that was the wrong button. What did I do here? Oh, there we go. Okay. The inverse sine of negative the square root of 3 divided by 2. And if I get that, I get negative 1.047. Okay. So let me just write that on the next page. So if I just blindly use my calculator without thinking about it, if I take the inverse sine of the square root, negative the square root of 3 over 2, I'll get negative 1.047 radians. So what is that? Is that, you don't memorize, is that pi over 6, pi over 4, pi over 3? It's not even it's in the fourth quadrant, but it's not, it's going the opposite direction. It's the negative answer. So that's not going to help me out a whole lot. There's two things. One, it's not in terms of pi, which a lot of times helps me figure out where I am. So the bottom line is, you can't just blindly use your calculator to figure out where the heck you are. So here's the right way to do it. So let me erase that. So these are great if you know how to use them, but with great power comes great responsibility. So, okay, so the answer was quadrants 3 and 4 for the first part. Okay, the second part is calculate the reference angle. So to calculate the reference angle, you just take, in this case, the reference angle, or I'm going to use theta, so, sine of theta. I like theta for angles. So if you want to find the reference angle, you just take the inverse, you do use your calculator, you take the inverse sine of the absolute value of the square root of 3 over 2. So the only difference is I take the absolute value of the number here. So I just make it positive. And if I do that, so inverse sine, so try this on your calculator, inverse sine of positive the square root of 3 over 2, square root of 3 divided by 2, and I get plus 1.04719 something. Okay, so that's my reference angle. Now, step number 3 is convert your reference angle to some, it's not really multiple, but I'm going to use the word multiple of pi. So to do that, all you have to do is you take your reference angle, which is 1.04719, divided by pi times pi. So I'm just multiplying by 1. But this part I do in my calculator, and that results in some number times pi. So if I take 1.047 divide by pi, which is on your calculator, you get 0.333 pi. And we say, oh, that's a third. So the answer, the reference angle in this case, in terms of pi, is pi over 3. So your calculator is not going to tell you it's pi over 3, which is what we're used to doing in pre-calculus. And you're saying, well, what if it's something like pi over, what if it's some 0.472983 pi? You know, not 0.33 pi or zero point 0.5 pi or 0.666 pi, you know, the normal things, or 0.25 pi, things that you can recognize as the fractions. Well, you just leave it as a decimal. But if it's something, if the decimal is something that looks familiar, or you can recognize this as a sixth, a fourth, a third, all those kinds of things, then convert it to a fraction. Otherwise, leave as a decimal point. Okay, so now we know the reference angle in terms of pi. And then the last step here, whoops, is you use the three formulas. So use the appropriate formula to find theta, or x. So the appropriate formula is if your solution is quadrant 1, then theta is equal to the reference angle. That's easy. In the second quadrant, theta is equal to pi minus the reference angle. In the third quadrant, theta is equal to pi plus the reference angle. And in the fourth quadrant, theta is equal to 2 pi minus the reference angle. So these are the four formulas you have. Since our solution is in Q3 and Q4, theta is equal to pi plus the reference angle, which turns in this case pi over 3. So for Q3, my third quadrant solution is pi plus pi over 3, which is 4 pi over 3. And my fourth quadrant solution is theta, oh yeah, that's right. Theta is equal to 2 pi minus pi over 3. So my second solution is going to be 6 pi over 3 minus 1 pi over 3, which is 5 pi over 3. So I'm converting this to a fraction with a decimal. So this is 3/3 pi plus 1/3 pi is 4/3 pi. This is 6/3 pi minus 1/3 pi is 5/3 pi. So those are my solutions, and that's the way you do it. So it's, you know, it's pretty mechanical. You don't have to think about units, circles. And the biggest advantage is when this is not a half, square root of 2 over 2, square root of 3 over 2, or one of the signs. And, you know, those are the solutions between 0 and 2 pi. You have an infinite number of solutions, but usually in these problems they say, you know, what are the extrema on this interval? They'll say usually between 0 and 2 pi, but it could be between 0 and pi and things like that. Okay, so we'll use that again in a second, but I just want to introduce you to it, and we'll get some more practice at going through the steps. That's what I used to do. Okay, so we're going to use that to, in this case, we're still not taking if I took the derivative of a function and the derivative was equal to that, and then I'm asked to find what are the zeros associated with that, what values of x does that expression go to 0. So in this case it's a quadratic equation in terms of the sign. So what we would do is so the question is, at what values of x or theta, I'll put question, this is or theta. I'm going to use theta once I solve it because I like theta. At what values of x is this expression equal to 0? Question mark. So what you would do is you'd factor this thing. So you'd have 4 times sine of x, and you'd have 3 times the sine of x. And since I have plus 1 here, I need to put plus 1 there and negative 1 there, so that when I use FOIL, you'll see I get 12 sine squared x minus 3 sine x plus 4 sine x, which is 1 sine x, and negative 1 times 1 is equal to negative 1. So there you go. So my solutions are going to be, this function is going to be equal to 0 when 4 times the sine of x minus 1 equals 0, and when 3 sine of x plus 1 equals 0. So I'm going to solve for the sine of x. Sine of x is going to be equal to 1/4. So this goes to the other side, divide by 4. Likewise, the sine of x is equal to negative 1/3. So to find the values of x, I have to somehow, I could take the inverse sine of 1/4 and I get one answer, but the reality is that between 0 and 2 pi there are two values of x where this goes to 0, where this is true, and there are 2 values of x where this is true. And they're not square root of 3 over 2 or half or square root of 2 over 2. So I can't use my unit circle here. So if you didn't know this other part, you'd be stuck. You'd be like, I can only do things that are, I like a roof at 25 degrees, so I can't do that. I can only handle 30 degrees. So, okay, I'll get somebody else to do that. Okay, so so what we're going to do is we're going to, I'm going to do the first one, and then I'm going to show you how to do it. Then I'll let you do the second one. We probably won't get to doing the second one until Monday. So here we go. Sine of x equals 1/4. I'm changing to theta because I like theta. It doesn't really matter what variable I use. I just can't handle. So the sine of theta equals quarter. Okay. What values of theta between 0 and 2 pi does this work? Question mark. Okay. Step number 1. What was step number 1? In which quadrants is the sign, in this case, positive? Okay. Which quadrants is sign positive? Okay, so mark. All students take calculus. So which one? Which quadrants is assigned positive? All. First one, yeah. Yeah, all students. So it's going to be this, so it's going to be quadrants 1 and 2. Okay. The second part is, I guess we calculate the reference angle. I think so. Okay. So the reference angle is going to be equal to the inverse sine of the absolute value of 1/4, which is just 1/4. So we plug that into our calculator. Make sure we're in radians. So the inverse sine of 0.25 is 0.2527 radians. Okay, step 3 was convert to some percentage of pi, some decimal times the pi. So to do that, all we do is you take the value that you get from your calculator, you divide by pi, and we multiply it by pi, but we just, the second part we just leave there. So what we're really doing is we're just doing this calculation. So divide by pi, and I get 0.0804 pi radians. That doesn't look like anything that looks familiar. You know, so because this is not 0.33 or 0.1666 or whatever, something that 0.25, we don't do it. We don't change it to some fraction of pi. I guess we could see if there's a fraction. If you change that, use your calculator. I'm not going to recommend this, but yeah, there is no. There is no fraction. So that's an irrational number. Okay, so the fourth step is to, where are we? Let's go back here. Fourth step is to use the appropriate formula. So the appropriate formula, since it's in the first quadrant and the second quadrant, one solution is that it's just the reference angle. So this is the first quadrant solution. So the answer is 0.0804 pi. And the second quadrant solution is going to be equal to pi minus 0.0804 pi. And that's 1 pi minus 0.0804. So all you have to do is take 1 minus your previous answer on your calculator, and you would get the second solution is 0.9196 pi. So those are my two solutions for this first one, okay, for the sine equals a quarter. So now what you want to do is do the same thing. So go ahead and we can have time to get started. So see if you can figure out what the solutions are for when sine of x is equal to negative 1/3 using the procedure we just outlined. Obviously the solutions are going to be in the third and fourth quadrant because the positive ones were in the first and second quadrant, so the negative solutions are in the third and fourth quadrant. You'll take the inverse sine of positive 1/3, whatever. So I think those are the answers. Did anybody get that? Anybody get that far yet? Let me make sure I didn't do anything wrong here. Yeah, I think that's right. So when you take the inverse sine of a third, what do you get? Did you get that part yet? What's that? 0.3398? Yeah. So when you take the inverse sine of a third, you get 0.3398. And if you divide 0.3398 by pi, you get 0.1082. And so that's your reference angle is 0.108 pi. So your third quadrant solution is 1 plus 0.108. So it's pi plus the reference angle. And then the fourth quadrant solution is 2 pi minus 0.108 pi, which is 0.189 1 pi, if I did that correctly. So if I plot this thing, let me plot the function, this function, and find out where the zeros are. So if I go to my graph, actually what I'm going to not find where the zero, yeah, I'm going to find where the zeros are, because we're not taking the derivatives yet. We're just trying to learn how to do this stuff. So 12 times the sine of x squared plus, what was the, it was 4 or 1? It was just 1. So it's going to be the sine of x minus 1. Okay, I think that's the function. And so if we look at it and we put the x-axis in terms of pi, like that. So it says, so between 0 and 2 pi, we have one intercept here, one intercept there, one intercept there, and one intercept there. So this one is the point, let me move this, where's my solutions here? So if I, yeah. So those are my solutions. So let's see if we can find them. So this one is the point 80804 pi. This one is the 0.92 pi. That's the second one. This one is the 1.108 pi, and this one is the 0.1891 pi. Okay, so these are the first two. These are the first and second quadrant solutions. These are the third and fourth quadrant solutions as far as the intercepts of that function. So we did it right. At least I did it right. So if you didn't get these answers, why don't you talk? How many people got that? Okay, so there's a few people who got it. If you're wondering how to get it, why don't you talk to them in study session? And if you still don't understand, I'll show you next time, which is tomorrow. Okay. Oh, as far as let me assign the homework. So there's the homework for this section. So that's assigned for today. Due next Thursday.